All right, so we are going to begin chapter 9. If you were here on Friday and did the gizmo, you already kind of have an introduction to what chapter 9 is. Chapter 9 is electron configurations. So this chapter, little to no math. All you really have to think about is things being in pairs, and what we're really trying to do. This is kind of another way to just identify where an element is located and what an element is. So when we look at electron configuration, this is more about helping us understand why elements bond the way they do, because we're really going to end up focusing on the outer shell electrons, even though at the beginning we're talking about all of the electrons. So our goals today, describe energy levels. You're also going to hear me call them quantum levels today. Sublevels, which will be the S, P, D, and F. And then orbitals are going to be the orientation of the sublevels. And then we'll actually talk about individual electrons and direction of spin and all of that. Southeastern's requirement is that, and they say to be able to draw orbital diagrams and write the electron configurations for elements 1 through 56. In reality, what you have to be able to do is recognize. So like if you see an electron configuration, be able to figure out what element it is. All right. So as we're going through this, today we're going to be drawing them and writing them. But beyond today, it's more about being able to see one and know what element it belongs to. So I want you to, for today, I want you to be able to draw it, just because I feel like if you draw it, you kind of get a better idea of what's going on with it. And then once we're past that point, then we can look at the multiple choice type situations and be able to figure out what element it is and start kind of troubleshooting to figure out what they are. Also be able to determine the number of core electrons, which are your inner electrons, versus your valence electrons, which are the, we've been talking about all year, which are your outer shell, your outermost electrons. From an orbital diagram, electron configuration, or the element's position on the periodic table. And then there's going to be three kind of rules that guide this chapter. Aufbau principle, Hund's rule, and Pauli exclusion. I'll get more into what those are as we progress through this. Chapter 9, yes. So going through this, where we start, we kind of talked about Niels Bohr earlier in the year, and talked about a Bohr model of a atom. You might have even drawn Bohr models before, maybe in middle school or something like that. I know Miss Nagel used to like to have her students drawing. I don't know if she still does because of curriculum changes and all of that. All right. But Bohr model kind of gives us a general, almost like a view of an atom, like a solar system, where the nucleus kind of represents the sun, and then the electrons are like planets orbiting around it. All right. It's a great teaching model, but as we've learned more about how electrons work and how atoms themselves work, it's not a realistic model. It's not a model that's totally true. What we've discovered is that electrons aren't necessarily in like a fixed orbit, but they have areas where they're likely to exist, which gets off into a little bit abstract. But in general, when we look at an atom, we think of it this way, but I'm going to try to shift the way we think of it a little bit
today. All right. So Niels Bohr, his model designed. It was a model where the electrons travel in a circular orbit, similar to planets orbiting the sun. You have all of this on your paper already. Electrons can only orbit at specific fixed distances from the nucleus. Now, that's something that we still know to be true. Electrons are not going to ever exist in between the energy levels. They can jump from one to the other, but they don't stay there. So they won't stay in between it, but they'll exist at each energy level. So one of the things that I want us to know, and you can write it on here, energy level N1 or quantum level 1 is the lowest energy. And you gain energy as you move outward. We have actually 7 energy levels. All right. Just like there's 7 periods on the periodic table. And that's kind of why we built the periodic table we have, is because we're recognizing 7 different energy levels, or 7 different quantum levels. So the further you are from the nucleus, the higher the energy of the electrons. So there are 7 energy levels, or 7 quantum levels in Bohr's model. That's why the periodic table has 7 periods or 7 rows. Now, looking at the drawing that I have, what do you notice about the distance between the rings as we get further out? They get smaller, they get closer together. So it takes more energy to go from N1 to N2 than it does from N3 to N4. All right. So as you get further out, it takes less energy to get to that next level. All right. So you can also kind of look at this like a ladder and notice that the rungs are not equal. They're spaced out. So again, it's a greater energy jump to go from N1 to N2, and then from N2 to N3, and so on. So the further you are away from the nucleus, the more energy you have, but the less energy it takes to go up one level or not. Must have missed a page. It missed a page. All right. So the energy levels. Energy and levels involved with these specific densities are called quantum numbers, or quantum levels. So we can have quantum level 1, 2, 3, 4, 5, 6, and 7. Those numbers correspond to the period So if you have an element that exists in period 6, its outermost energy level is going to be quantum level 6. That's where the valence electrons exist for that one. It will have all of the ones underneath it, but the outermost will be that one. All right. So the energy is fixed or quantized for the electrons in each level. Electrons cannot exist between the orbits, only in the orbits or only in the levels as we're going through it. So what we want to do, or what I want you to do, maybe not so much think of it as a solar system type model anymore, but instead we're going to think of it as regions where the electrons are possibly at. If you've taken psychology, you might have heard of Schrodinger. Schrodinger actually wasn't related to psychology, he was related to physics. What his whole Schrodinger's cat thing was talking about is we can predict either a location of something, where it is right now, or where it's going to be. So that was the whole idea of you didn't know if the cat was dead or alive inside the thing. So what we're looking at is we can either have an idea of where the electrons are supposed to be or where they're going to be. All right, so that's kind of relating to this. All right, so we have a newer model that replaced the Bohr model. However, it's not a very good model to draw or to teach from. That's why we still use Bohr model. We call it the quantum mechanical model, or another name for it is the electron cloud model. All right, they essentially are the same thing. But so instead of having orbits, they call them orbitals. Orbitals indicate a probability map of where an electron is likely to be found. It does not project the exact path of any electron. So kind of a difference when you're comparing an orbit to an orbital. An orbit represents a circular map or a circular path or an elliptical path if you're looking at planets. An orbital is just a probability map. It's just somewhere where we can say, okay, there's something supposed to be there. We don't know exactly where. All right. So instead of calling them energy levels, we call them principal quantum levels. All right. So principal quantum numbers are going to be N1, N2, N3, N4, N5, N6, and 7. Yes?
Why does period 4 count as only one quantum level if it can be either +4 or -4?
Okay. That's group 4. Period is across. So you only have one energy level per row. So every time, so the further you are, so as you go down the periodic table, everything on this row has more quantum levels than everything in this one, and so on. So you get fewer and fewer. The whole thing of plus and minus has to do with outer shell electrons only, and it means they can either lose or gain that many electrons. All right, so when we're looking at the quantum levels, each quantum level can hold a certain amount of electrons. The higher the principal quantum number, the higher the energy. I've already talked about that. Quantum levels are the same thing as energy levels. You'll hear me refer to them both, and there are 7 levels. Something that I want you to know. So I'm going to go ahead and write the rest of them. All right. So
each energy level can hold a specific amount or a maximum amount of electrons. So when we're looking at N1, quantum level 1 can only hold 2 electrons. Notice how many, if you look at the periodic table, how many elements are in period 1? 2. See the relationship? 2 electrons, 2 elements. All right. Period 2, or quantum level 2, can hold up to 8 electrons. How many elements listed in period 8? Period 2? 8. All right. Now, it gets a little bit funky from here on because technically on row 4, that center area where the D block is, where the transition metals are, those are technically going to be filled when you're on period 3. So things like SC, TI, V, CR, FE, we're going to be filling energy level 3 as we're moving forward. So energy level 3 can have 8 or up to 18 electrons in energy level 3, depending on where it's at on the periodic table. You should also start noticing on the side, notice these numbers. When it's just up to argon, energy level 1 has 2, energy level 2 has 8, energy level 3 has 8. But then when we get down to period 4, quantum level 1 has 2, quantum level 2 has 8, quantum level 3 has 18, and then it goes to 8 for period 4. And then we'll start seeing some shifts as we go. So quantum level 4 can have 8, 18, or actually 32. So those are kind of the fill points, 8, 18, and 32. N5 is exactly the same as N4. N6 goes back to 8 and 18, and N7 can just hold 8. All right, and we're gonna start seeing why in a little bit, and I'm gonna kind of go over that as we're moving forward. So, all right. So the next slide that you should have like a blank periodic table. All right. So I'm going to introduce a term in a minute called a subshell or a sublevel. And there are 4 sublevels that we identify. We have the S, P, D, and F. Each one of these represents a region on the periodic table. So the first sublevel is the S sublevel. So when we're talking about the S, it's the first 2 columns of the periodic table, and then it also includes helium. Remember that I said hydrogen and helium hydrogen specifically can be in 2 places on the periodic table. Technically, helium can as well. Helium can also be above group 2 because it has some properties like group 2 as well. But it doesn't form ions. That's why we keep it on the other side. All right. So now, on yours, you can actually do this. So we can have 1s. If it's on the second level, it would be labeled as 2s. If it's on the third level, it would be labeled as 3s. Fourth level, elements would be 4s, 5s, 6s, and 7s. All right. So you can kind of label them like that. So, but that whole region is called the S block. The second region is the p orbitals, or p sublevels. P sublevels is that region of period 2 to period 7, starting with group 3A all the way to group 8A. So just like before, what row does the P start in? First row or the second row? Second. So we don't start labeling with 3P. I mean, with 1P, we start labeling with 2P. 3P, 4P, 5P, 6P, 7P. Also note some trends to kind of notice. Notice how many columns the S represents. Represents 2. That's going to relate directly to how many electrons it can hold. P represents 6 columns. It's going to relate directly to how many electrons it can hold, which is 6. All right. Now, the next sublevel is called the D sublevel. D is going to be quantum level n minus 1. So it's always going to be 1 less than the row it's on. So instead of starting with 4D, I would actually start with 3D here, 4D here, 5D, 6D. So remember I said you don't start filling like you can still be filling on the 3rd energy level when you're in the 4th row. Notice that there are 10 electrons in that region, or 10 columns represented in that region. So that means we're going to be dealing with 10 electrons. And then the last region is the F block, or the F sublevel. F is kind of weird because remember, we show it as being down here, but remember the periodic table looks more like this one where it's shifted inside of there. All right, so that represents a series of 14 columns. We call that F. And so just like the D is n minus 1, F is n minus 2. So technically this is period, let me do this. This is 1, 2, 3, 4, 5, 6, 7. Remember that this F block is actually on periods 6 and 7. So it's n minus 2. So this is going to be 4F. And this is going to be 5F. And that's where we can get up to 32 electrons in periods 4 and 5. All right. So the next slide is going to show you one method, the way the book teaches you to do this. I'm actually going to kind of teach you a different method to do this as we're going through it. So I do it just a little bit different, counting electrons, and for me it's a lot easier of a way than what the book shows us, but some people like the book method. All right. So actually there is a different one. How can the slides get out of order? All right. Some of the slides kind of got out of order. I'm not sure how that happened. But there are 3 rules that guide electron configurations. The first one is called Aufbau principle. Second rule that guides electron configuration is called the Pauli exclusion principle. So I'm going to write this next to it. Aufbau has to deal with fill order. Pauli exclusion principle deals with direction of spin. And then Hund's rule deals with fill order and spin. So first rule is, what do we fill first? You know, like energy level 1 gets filled before energy level 2, 3, and so on. All right. Pauli tells us that the electrons have to spin in opposite directions. And then Hund's rule tells us that as we're filling, we have to fill one direction before we fill the other within a certain sublevel. So as we're looking at these, I'm going to take each one individually and kind of go from there. All right, so I'm going to start with Aufbau principle. The word Aufbau is a German word that means build up or create. So that's directly translated is kind of like counting in order. All right. So according to Aufbau principle, electrons occupy the orbital of the lowest energy first. So if we're looking at the lowest energy level, what would be the quantum level that's going to be the lowest? 1, right? And then beyond that, S is going to be lower than a P, and a P is lower than a D, and so on. All right, so the fill order is as follows. So we start with 1s. Then we're going to fill 2s. Then we'll fill 2p. Then we'll fill 3s. And then 3p. And then here's where the order starts changing a little bit, because it does some things we don't expect. We get 4s, but what's right next to 4s? 3d. So that's the next thing we fill. And then we go to 4p. And then we have 5s, 4d, 5p. And then when we get 6s, 4f, 5d, 6p, and so on. And so the fill order would be like this. Another way that we can look at this, and this is the way that a lot of textbooks will teach you the fill orders. So they make you create a chart like this. The reason why I don't like this one is because you have to write this chart every single time to do it. All right. So now, the way that it says to do this is, as we're filling electrons, we start from the upper right and draw an arrow down to the bottom left, which, great in theory, it confuses the hell out of me, so I don't use this method. I'm going to show you a little bit different method using just the periodic table in a minute. All right, so it would say we fill 1s first, and then after we fill 1s, we fill 2s. Then we fill 2p, 3s, 3p, 4s, 3d, 4p, 5s, and so on. Like I say, I'm not a fan of this one. What I do is I just count electrons across the periodic table, and I'll explain that as we kind of go into it. All right. So,
I'll leave this up because I know I covered that one up on yours. All right, has everybody had enough time to copy that? All right, so like I said, I'm not gonna show that method, but if you watch videos like Melissa Maribel or Tyler DeWitt or any of the videos to help with this, they may actually use that method. So I want you to be familiar when it pops up. I'm going to show you a little bit different way. All right, so now let's talk about the orbitals a little bit real quick. So just to make it a little more interactive on the notes, I actually left some blanks for you. But when we're talking about the subshells or the sublevels, the first sublevel or the smallest sublevel is the s orbital. The s orbital is the lowest energy orbital. It can only hold 2 electrons. Something that I didn't put in my notes, but you're going to hear me talk about this. Since the s orbital is the shape of a sphere, and that's kind of where they get the s from, is that it is spherical. When you look at a sphere, does it look different depending on the direction you look at it from? No. So a sphere only has one orientation. We can only, no matter which way we turn it, it looks exactly the same. And that spherical orbital can only hold 2 electrons in it. All right. And so if we're looking at a XYZ axis, no matter which direction we're orienting that axis, it looks the same. All right. So again, s orbital is the lowest energy, or S sublevel is the lowest energy. It can only hold 2 electrons. It's considered to be a sphere, and it only has one orientation. P, which they have denoted it that it kind of looks like a peanut. Sometimes you'll see a textbook refer to it as a dumbbell, but it kind of has the shape of a peanut. Notice there's 3 different directions we can turn this, or 3 different orientations. We can lay it on the x-axis, we can lay it on the y-axis, or we can lay it on the z. All right. So there's 3 different orientations. Each orientation can hold 2 electrons. So that means that the p sublevel can hold 6 electrons total. Now, I'm going to start relating this to the periodic table. So if I'm looking at something on 3p, notice I have 1, 2, 3, 4, 5, 6. So argon would have the 6 electrons. Aluminum would only have a p1. So as we're going across, we would add each one an electron. All right. So we can have a px, a py, or a pz orientation. All right. Now, the d orbital, or d sublevel, has 5 different orientations. D, the kind of common name for it is a double peanut, because it looks like 2 peanuts laid across each other. Well, there's one that looks more like a flower. So D is double peanut. It has 5 different orientations, so we can have it kind of on the Y and Z. So we have the DYZ.
We can have it on the x and the y, so we have dxy. We can have it on the x and the z, so we have dxz. And then we can have it kind of occupying some different, like, in-between regions. So if you kind of think of these things like balloons, and you can think how you can tie these balloons together and fill up the different space in a 3D model. So you have one that's called, and I don't expect you to memorize these. You're never going to be asked to know these orientations. But it's the dx2 minus y2. And then there's the dz squared. That looks a little bit different than the rest. It kind of looks like a P with a donut around it. And again, you won't be asked to draw these pictures. I'm just trying to give you an idea of how we do this in a space model. How all of these could stack on top of each other and not occupy the same space. Or be able to occupy the same space. That they're not penetrating each other. All right, so again, the d orbital has 5 different orientations. Each orientation can hold 2 electrons, so 10 electrons total. Now again, I'm going to come over here to the periodic table. If you count from here to here, how many columns is that? So from SC to ZN, it's 10. So there's 10 possibilities. So this would be like ZN is going to be represented by 3D10. All right. Nickel would be represented by 3D8. And so on. All right. The last sublevel is the F sublevel. It has 7 different orientations. I'm not going to go into the 7, but you can kind of look at them. There are some funky shapes in there and all of that. The F kind of stands for flower, because somebody one day thought these kind of look like a flower. That's fine. IUPAC disagrees. IUPAC disagrees. That's the people that kind of give us the names and the rules. IUPAC, International Union of Physical and Applied Chemists. All right, 7 different orientations. 2 electrons each, so 2 times 7, 14 total electrons. Now, depending on the periodic table you get, sometimes you'll see a little gap right here. That LA and AC actually are part of, well, actually, LU and LR are part of the D block. So what you're looking at is you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 columns represented. And then these 2 are part of D block. All right, because they actually fit in that little section that's removed. All right, so be careful on that one when you're counting. I'm not going to ask you to do any F blocks other than maybe in a homework just recognizing something. All right. All right. So we talked about Aufbau. Aufbau says we fill 1s before we fill 2s, before we fill 3s. Before we fill 2p, then 3s, 3p, so on. The next rule in the next person is Pauli. And so we have quantum level, which is numbers 1 through 7. We have sublevels, which is S, P, D, or F. And then we have orbitals, which would be like the PX, PY, PZ. An orbital may describe at most 2 electrons. So an orbital can only describe 2 electrons. And those 2 electrons have opposite spins. So if you were doing the gizmo on Friday, you might have saw where they were representing electrons as arrows. Each arrow represents 1 electron. So an up arrow means it's spinning in one direction. The down arrow means it's spinning in the opposite direction. And so that box represents 1 orbital in a certain sublevel. All right. So when we talk about spin, and if you're talking to a physicist or a quantum chemist, they might talk about it spinning clockwise or counterclockwise. Sometimes they'll show it as a plus spin or a minus spin in certain notations, things like that. We're going to represent it by an up arrow or a down arrow. Don't really need to get too deep involved in that. So again, we fill an orbital with an up arrow and a down arrow. And each orbital can only hold 2 electrons. So this goes with the orientation. So how many orientations did I say an S can have? S. Look back at your notes. 1. So an S will only ever be represented by 1 box. How many orientations can a P have? Look at your notes.
I don't know. I don't have that.
3. So a P orbital would be represented by 3 boxes. All right. Each one containing 2 for a total of 6. So I can have 2 electrons here, 6 total here. And then when we get to D, remember D can hold up to 10 electrons. So how many boxes would we have? 5.
Okay, so I think this might be a silly question, but how do you just have to know that it's 3? Can you figure out what you're doing?
Well, if you know that each one of those boxes can hold 2 electrons, and I know that there are 6 columns in the P, that means I have 3 orientations, or three boxes of 2.
Okay, so
D has 10 columns. Each one can hold 2. So 10 divided by 2 is 5.
okay.
All right. And then F, we said F can hold up to 14 electrons.
7.
So 7 boxes. Hopefully you never have to draw an orbital diagram for an F orbital thing, because these can get really, really cumbersome. Some of you might even mention on Friday, I'm tired of drawing these or writing these. All right. So I don't know if it was this class or second period that said it, but one period mentioned it. So, all right. So, if I had to draw an orbital diagram for something, so I'm just going to pretend I'm drawing something in the 4th energy level. All right. So, and I'm only looking at the 4th energy level right now. So I can have 4s, 3d, and 4p. So in 4s, I can have a box here. 3d, I can have a box. I have 5 boxes. In 4p, I have 3. So if I'm filling this in order, and let's just say that I am looking at arsenic, AS. Where is arsenic related where is arsenic on the periodic table as to S, D, P, or F? It's in the P. So I know that I'm going to end somewhere here. All right. So filling this up, I'm past 4S, right? So that means that's completely full. I'm past 3D because I'm past Zn on the periodic table. So that means I've used those 10 electrons. Now, how far am I in to the P block?
1, 2, 3.
3. So that means I have to represent 3 electrons into P. I haven't given you Hund's rule yet, but Hund's rule basically tells us we have to fill in one direction before we fill in the other. So that's why I have 3 ups.
So like say it was 2, you'd only have 2 ups.
I would only have 2, and then the third box would be empty. So if I was looking at germanium, Ge, I would only have an up and an up. If I was looking at Se, I would have up, 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 and the first box is down.
Okay. Those are arrows.
Those are arrows. I only draw half an arrowhead because I don't have to pick my marker up.
Oh.
All right. All right. So, kind of already talked about this and already mentioned this, but Hund's rule says electrons occupy orbitals of the same energy in a way that makes the number of electrons with the same spin and direction as large as possible. So another way to say that is we fill electrons in the same direction first. So we will fill within a certain sublevel, we will fill all of the electrons in one direction before filling the others. So if this represented, let's just say this represented an element in 3P. And let's say it was, let's say that this is representing oxygen. Well, sorry, 2P. So let's do 2P and say this is oxygen. All right. How far is oxygen into the P? 4. So that means I need 4 electrons. So 2, 3. Where am I going to put the 4th electron? Down in the first one. Now, theoretically, it doesn't matter if I put the down here, here, or here. I just have to only have one down, and that has to be the 4th one I fill. All right. So I could have it in the Z box over there. I could have it on the far box instead, but I can't start doing the downs before I did all of the ups.
Wait, I understand the arrow stuff, but what is the 3P and the 2P like? What is that?
Second row, P block. So
I
oxygen.
thought it was the first row because the P doesn't have the first row.
Oxygen is in the second period, right? So that's why it's 2P. All right. P only starts at number 2. Just like D doesn't start until the third period. All right. So there are some exceptions. Some electron configurations differ from those assigned using the alpha principle. Those mainly occur in the D block. There are a couple of them that when you're going to end up with say we end up with an element that's going to end up being like 4D. All right, we're actually going to steal an electron from the 5s and put it in there. So instead it would be a 5D, but it would be like, it would be 5s1 4D5 instead of 5s2 4D4. You're not going to see these in our work. But there are some exceptions that sometimes if you look it up, it's going to give you something different than you expect. And that's just a way of, it's an accounting thing that they do. In higher level chemistry, we account for something called paramagnetic and dimagnetic. And that just helps with that description, that we don't need to know that yet. All right, so this does lead to some funky ways that they will bond with each other and all of that, but that's just kind of where that is. All right, so electron configuration shows the occupation of orbitals by electrons for a particular atom. Each subshell can hold a maximum of 2 electrons, and the electrons in a subshell must have opposite spins. That's the Pauli principle. All right. So if I were writing an electron configuration for helium, what row is helium on? It's on the 1 quantum level. Technically it's in the s block. And how many electrons is it going to have? 2. So I'm going to say 1s2. That's how I would represent helium as an electron configuration. Now let's do a little bit different. Let's look at magnesium. What period is magnesium on? It's on the 3rd period. So that means that I had to have filled all of the 1st period, all of the 2nd period, and then I'm starting into the 3rd period, so I have 3s. And how many places is it into the s? 2. So that is kind of like the, it'd be kind of like the roadmap to magnesium. All right. I have to go 2 spaces into 1. I have to go 2 spaces into 2, then 6 more spaces, then 2 spaces into 3. All right. So that's one of the ways that we're going to do this. This is called a regular order configuration. All right. If I was representing this,
Why couldn't you just do 3s2?
because 3s2 only tells me about the outer shell electrons. I want to know about the inner shell too. I want to know where every electron is located. That's what this is telling us. It tells me I have 2 electrons on the 1st energy level. It tells me I have 8 electrons on the 2nd energy level and 2 on the 3rd. And it tells me exactly where to expect them. All right. So we call that configuration a regular order configuration. I could represent this as an orbital configuration as well. So helium's easy. Orbital diagram for helium looks like that. Orbital diagram for this one, I have my 1s, I have 2s, I have 2p. I'm not going to draw the full boxes. I'm just going to do dashes for it. And then I have 3s like this. So 1s2 means it looks like that. 2s2, I have 2 electrons in that sublevel.
2p6, and then 3s2. All right. So both of these say the same thing. This says the same thing. They help me see different things about it, but they tell me the same thing. So, in your packet, you should have a sheet that looks like this. All right, we are going to look at arsenic first, and we're going to kind of walk through what we're expected to be able to recognize and do with these. You're probably going to want to have out a periodic table. So have out your periodic table reference pack. I'm going to show you the way that I count these. And we'll go from there. All right. So does everybody have what they need off of this slide? Okay. So let's look at arsenic together. On your periodic table, I want you to find arsenic and put your finger on it. All right. We already talked about arsenic a little bit because I used it as an example earlier. But where is arsenic located? It's on the 4th row. Which block is it in? It's in the P block. And how many spaces is it in? 3. So here's what I know about arsenic. I know that arsenic is going to end in 4p3. All right. Now, in order to get to arsenic using my periodic table as a roadmap, I have to go through hydrogen and helium, right? So that means that I've went through 1s2. I have to go through lithium and beryllium, right? So that gives me my 2s2. I have to go through neon, and so that gives me my 2p6. All right, so I'm still on the 2nd row right here. Now, when I go through sodium and magnesium, what does that cover? 3s2. All right, aluminum to argon, what does that cover? 3p6. All right, now, potassium and calcium, 4s2. Now, from scandium to zinc is going to be 3D. And what number am I going to write next to the D? 10. Because we went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. And then I go 3 places in, 1, 2, 3, and that's why it's 4p3. Now, if I was being asked to identify this as a multiple choice, and I would say they give me several different electron configurations and say which one represents arsenic, what's the first place that I'm going to look to see to eliminate responses? I'm going to look at the end. I'm going to look at that 4p3. If it doesn't end in 4p3, I'm automatically eliminating it. If I have 2 of them that end in 4p3, I'm going to make sure everything below it is full. So the maximum an S can have is 2, the maximum a P can have is 6, the maximum a D can have is 10. So I'm not
writing this out every time. I'm trying to look for how would I identify this in a selection of choices. All right, so now, so this again is called our regular order configuration, our standard configuration. All right, now you have more on your sheet. So let's. All right, let's see how we go from regular order to orbital. Now, I don't need my periodic table once I have my regular order configuration written. I don't need that anymore. What I need to know is, so 1s we said only has one orientation, and s only has one orientation, so that represents my 1s, 2s, one orientation. For 2p, how many boxes or blanks do I need? 3. So I'm going to draw little lines in between it. All right, what comes next? 3s. It's one blank. 3p comes next. 1, 2, 3. And then 4s, 3d, 1, 2, 3, 4, 5. And then I'm going to write my 4p down here. All right, so now notice that everything up to 4p is completely full. So that means each one of my blanks is going to have an up-down arrow. So on this part, I'm only worried about Pauli and Aufbau that I'm just filling in the right order. All right. Now, for my very last one, I have to worry about Huns. Hun says that I have to fill all the ups before I fill the downs. So how should my 4p look? Up, up, up. Now, this is just kind of a little bit of a mental exercise, but look at your periodic table. How many electrons would you expect a neutral atom of arsenic to have? How many electrons would a neutral atom of arsenic have? 33. Do me a favor. Add up all your exponents on your regular order.
It's going to be 33.
It's going to be 33. Then count your arrows. How many electrons do you end up with?
33.
33. So all we're really doing with this, all they're really doing with this is counting electrons, but they're also telling us where these electrons are located. All right, and what there is. Now, so earlier you were asking why can't we shorten this? There is a way to shorten it. There's actually 3 different ways to shorten it. Noble gas configuration. So find arsenic again on your periodic table. And I want you to find the noble gas on the period above arsenic.
Well, I don't know if we that.
All right. The noble gas on the period above arsenic is noble gas. That's the last column. So group 8A is your noble gases. Argon is on the period above arsenic. So when I write argon in brackets like that, essentially what I'm saying is, where does argon end? It's 3p6, right? So whenever I put argon in brackets, I am saying I know everything right here because that represents argon. So I can say argon, and then I just put what comes after it. 4s2, 3d10, 4d3. All right. So again, this says the same thing as this, but it allows me to look at it a little bit differently. And this says the same thing as the other two. It just allows me a different way to look at it. So when I write a noble gas configuration, what shell or what energy level am I most concerned with? Which electrons am I concerned with when I'm writing a noble gas?
The ones that come before it in a period.
Kind of concerned with the outermost electrons, or the last few electrons, right? Yes. It might give you the noble gas configuration, and if I ask you, well, it'll give you an element, and it'll give you choices of 3 or 4 different ones, say which one's the right. All right. Or it'll give you a noble gas configuration and say what element does this represent. All right. Now, valence shell configuration. What's the maximum number of electrons an outer shell can hold? What's our goal to get to for electrons in the outermost shell? It's called the octet rule. 8. Remember, when we're bonding, we're always trying to get to 8 one way or another. That's the whole thing about ions. Ions get to 8 electrons. Covalent bonding gets to 8 electrons. So valence shell can only have 8 electrons. What 2 sublevels add together to make 8?
Wait, what?
What are my sublevels again?
I don't even know.
How many electrons can S hold? How many electrons can P hold?
PD. What he said to make 8.
All right, so what? S and P. So looking at my noble gas configuration, if I'm looking at only my valence shell, what would my valence shell represent? The S and the P, because that can total 8. Now in this case, it's only totaling 5. So how many electrons does arsenic have in its outer shell? 5. We learned that way back just because it's in column 5A. And it makes
So
it
why do you
negative.
have to ask me all that stuff to get that?
Because I'm trying to help you make connections. So all of these, so far, everything is telling me the same thing, just in a different way.
So to get the valence shell configuration, you have to get the noble gas.
So, well, you don't have, I mean, at some point when you recognize what it is, you already understand. I understand when I'm just being asked valence shell, I know that arsenic is in the 4th period, and I know it's only going to include the electrons in the S and the P. So I know I have 2 electrons in the S and 3 electrons in the P. All right. I don't have to go through every step to get there, but I want you to see the connection from one step to the next. All right. Now, if I'm just looking at the valence shell, again, what quantum level are we in? What energy level? The quantum level is just energy level 4. So my valence shell is energy level 4, or quantum level 4. All right. Now, So ultimately, we're getting down to little less and less information. How many electrons in my valence shell again? 5. Now, I don't remember if I taught y'all dot diagrams or not yet. But a dot diagram, we take the chemical symbol for arsenic, which is AS. If I wanted to show this as a dot diagram, how many dots would I put around arsenic? 5. Because a dot diagram only shows the outer shell electrons. All right. So let's kind of work backwards here. So the one at the bottom of the sheet is potassium. So let's just look at the dot diagram of potassium first. Where is potassium located on the periodic table? 4s1. So how many dots would I have around potassium? Just one. All right, so that's what my dot diagram of potassium looks like. Ultimately, that's what we're trying to get to. All right, so potassium is located right here. So what do I know that my regular order configuration has to get to?
4s1.
All right, before that, I know I have to fill 1s, 2s, 2p, 3s, P. So if I fill 1s, how many electrons do I have? If I fill 2s, how many do I have? If I fill 2p, how many do I have? There's my electron configuration for potassium. All right, so what I would like for you to do, based on what we did on the one before that, I want you to create the orbital notation for it. And I want you to do the orbital notation, the noble gas, valence shell configuration, identify what is our valence shell, and how many valence shell electrons, and we've already done the dot diagram. Yeah, you always look at the noble gas on the period above. So even if you were on a noble gas, so if we were looking at xenon, we would put krypton in brackets and then whatever's else behind it. All right. So just to make sure we're on the right. Wrong thing. Just to make sure we're on the right track. Double check your orbital diagram. It should look something like that. All right, the 4s can be right up next to the 3p. That doesn't matter. But you should have 2 in the 1s, 2 in the 2s, 6 in the 2p, 2 in the 3s, 6 in the 3p, and it kind of got blended together. That's actually 2 different arrows there. So that's a down and an up like that. Yes?
For orbital notation, you have to put 1s, 2s, 2p.
I do that to I do that just to help me know what I'm feeling at that point.
Because you know that
If you know the order, I would say that you don't have to write it every time. It just helps for clarification. Like anytime you see it on a answer choice, it's going to have it labeled like that or something similar. All right. Again, today is probably the only day that I'm going to ask you to actually draw these. After that, it's just recognizing what they should look like. All right. Now, for noble gas consideration, noble gas configuration, what am I going to be looking at? What element would represent the row above potassium? It's argon again. All right. What else am I going to write? Valence shell configuration. It's just 4s1. Notice I don't have anything in the P this time, so I just write 4s1. What valence shell are we in? What quantum level are we in? We're in the 4th quantum level. How many electrons in the 4th level? And so the electron dot diagram looks like that. All right. We are going to start tomorrow with the other two, barium and xenon. For the orbital notation, if you want to, because both barium and xenon, notice that they are further down the periodic table. All right? So if you want to represent an orbital notation by showing it kind of like a noble gas, if I wanted to show this one like that, I could just show whatever's in my I could just show it like that. All right. So we can shorten the noble gas. We can shorten the orbital. Just show the last part of the noble gas configuration. So like if it was 4s2, 3d, 5, I would show the 4s and the 3d. Something like that.
Are we gonna do the other two tomorrow?
Yeah, but that's where we're starting tomorrow. So I want y'all to try it on your own, and then we'll go over them tomorrow.
Mr. Martin, the quiz on the gizmo, it wouldn't let me take the quiz. After I tried to turn it in.
It ended at a certain time, I think. I can reopen it if you need another shot.
I did the thing, I just didn't.
Okay, I'll look at it.
Okay.
Oh, you know what? The quiz, you need to make sure you go back into Clever. Sometimes it logs you out.
Okay.
So,
I'll just go back and
yeah. I'll let me double check it, and I'll let you know tomorrow.
Okay.
If it was argon,